Hello. In this video, I'm going to give you an example of calculating some interesting quantities when we have to use either current or voltage division and we have to identify if resistances are connected in series or in parallel. So let's go ahead and look at the topology, the circuit topology that we're given here. We have a 25 volt ideal voltage source, and then we have four resistances connected, 12 ohms, 8, 2, and 6. The main question that we want to answer here is we would like to find the voltage V right here, which is the voltage drop across the 8 ohm resistor. Now, there are a couple of different ways one can think about this problem. First, I will give you a common mistake that many of you might at least think about making, hopefully you won't, in trying to solve this problem. But I've seen it many times in my career in teaching this type of circuits that I think it's worth mentioning. And then once we cover that, I'll be able to give you the correct solution and why that's the case. So first, the mistake. By just looking at the circuit, one might simply say that I can apply immediately the voltage division formula. After all, I have 24 volts right here. I have a 12 ohm resistance here. I have an 8 ohm resistance there. Why can't I simply go ahead and say that V, the voltage drop that I want, from voltage division will be equal to the total voltage, 24, the resistance that I want, which is 8, divided by the total resistance, which is 12 plus 8. So, in volts, of course. So there is one, let's say, superficial way of thinking about the circuit that would probably lead you down the path of writing the equation you see right here. The easiest way that I can explain why this is wrong is by reminding you that the voltage division formula requires that the resistances are connected in series. So before you are allowed to write this formula, you should be asking yourself the question, are the two resistances, and specifically the 12 ohm resistance and the 8 ohm resistance, connected in series? You might say, well, I'm not sure. I don't know. They seem in series, but maybe not, maybe yes. In situations where you can't immediately tell what's going on, you should apply the current test. Just as a reminder, the only sure way you can apply here, the only bulletproof way you can apply here is by asking yourself the current question. If a current flows through the 12 ohm resistance, will it necessarily go through the 8 ohm, or does it have other options? If you're the current right here and flowing through the 12 ohm resistance, you're going to reach this essential node of the circuit, and then you can either go down or you can basically go to the right. So precisely because of that choice, precisely because of the existence of that node that will allow the current to split, the two resistances are not connected in series, and therefore applying the current division, the voltage division formula you see right here would have been totally incorrect. That formula requires series connection, as I'm writing here, which means it requires same current through the resistances. That's very important to keep in mind because this is something that you will see multiple times over and over again. So now let's go ahead and solve the circuit the correct way. It's still okay to apply some voltage division formula, but first we have to combine enough resistances in our circuit to ensure that what we have is indeed two resistances connected in series. So I can start from the other end of the circuit, perhaps by first considering these two resistances and asking the question, are these resistances in series? If the answer is yes, they are, because any current that will flow through this resistance here, the 2 ohm resistance, would have really no other way except to continue downwards through the 6 ohm resistance. And that means that these two resistances are indeed in series, and therefore they can be combined. So you can consider this resistance here literally as one resistance with a value of 2 plus 6, or simply 8 ohms. Now, that resulting resistance is between this node here and this node here. So that resulting equivalent resistance of 8 ohms connects these two red nodes. But there is an additional resistance also between these two nodes. I'm going to put it here with blue so you can see it more explicitly, is this 8 ohm resistance. So this 8 ohm resistance is between the two blue nodes, and these two blue nodes are identical to the two red nodes. So the two nodes here are connected together, and the two nodes here are connected together, making the 8 ohm resistance in parallel with the other 8 ohm resistance that we just found right here. So the two 8 ohm resistances, that one that used to exist, plus the resulting 8 ohm from combining 2 and 6, are indeed connected in parallel because they share the same nodes and therefore the same voltage. So that means I can actually replace them with an equivalent resistance, which I will call here Req. So Req is going to be equal to the one resistance I found, the 8 ohms, in parallel with the resistance that already existed, the other 8 ohms on the circuit. If you do this calculation, this result is of course equals to 4 ohms. And we learned in theory that when you're combining two resistances in parallel that are identical, you get half of the resistance. So now I can redraw my circuit like this. I have my 24 volts voltage source, nothing happened to it. I have my 12 ohms resistor, nothing happened to it. And now between those two blue or red nodes, I have my new found Req right here. And it's hopefully obvious that this node here, which I'm calling A, is this node here, A. And this node here, which I'm calling B, is obviously this node here that I'm calling B. Essentially, I replaced these combinations of resistances with Req. So now, of course, this voltage here, V, is exactly the same as the original voltage right here. That was also the voltage difference between nodes A and B. So now I can go ahead and apply the voltage division formula correctly this time. So I can say that V will be equal to the total voltage 24 times the resistance that I want, which is Req, over 12 plus Req. And of course, indeed, those two resistances, the 12 ohms and the Req, are exactly the same, are in series because the current is exactly the same through both of them. So from there on, you just have the numerical calculation to carry out. So you will have the 24 times the Req, which is equal to 4, divided by 12 plus 4, or the result of this is going to be equal to 6 volts. So once again, I would like to emphasize that applying the voltage or the current division formulas is a great tool, and you should be utilizing it, but you need to make sure that the resistances are indeed in series or in parallel when you do so. So thank you very much for watching this video. We will see you next time.